Hello students, welcome to the world of intellectual sub. Students, today we are going to study units and measurement in physics. So this is a part 2. If you are new to the channel, please subscribe the channel for more such videos. Let's start. Rule for arithmetic operation with significant figures. The result of a calculation involving approximate major values of quantities must reflect the uncertainties in the original measured values. It cannot be more accurate than the original measured values themselves on which the result is based. In general, the final result should not have more significant figures than the original data from which it has been obtained. Thus, if mass of an object is measured to be say 4.237 gram, that is the fourth significant figure in this number, and its volume is measured to be 2.51 centimeter cube, then its density we measure arithmetic division is 1.68804780.876 gram per centimeter cube, that is up to 11 decimal places. It would be clearly absurd and irrelevant to record the calculated values of density to such a precision with the measurement on which the value is based. Have much less precision, the following rules for arithmetic operation with significant figures ensure that the final result of a calculation is shown with the precision that is consistent with the precision of the input measured values. In multiplication or division, the final result should retain as many significant figures as are there in an original number with the least significant figures. Thus, in the example above, density should be reported to 3 significant figures. Here the density is equal to 4.237 gram upon 2.51 centimeter cube. So this is equal to 1.69 gram per centimeter cube. Similarly, if the speed of the light is given as 3.00 into 10 raised to power 8 meter per second, that is up to 3 significant figures, and 1 year is equal to 365.25, that is days, has 3.1557 into 10 raised to power 7 seconds. There is 5 significant figures. The light year is 9.47 into 10 raised to power 15 meter. In this, 3 significant figures are considered only. In addition or subtraction, the final result should retain as many decimal places as are there in the number with the least decimal places. For example, the sum of the number 436.32 gram, 227.2 gram and 0.301 gram by mere arithmetic addition is 663.821 gram, but the least precise measurement is 227.2 gram is correct to only one decimal place. The final result should therefore be rounded off to 663.8 gram. Similarly, the difference in length can be expressed as 0.307 meter minus 0.304 meter is equal to 0.003 meter is equal to 3 into 10 raised to power minus 3 meter. Note that we should not use the rule 1 applicable for multiplication and division and write 664 gram as a result in the example of addition and 3.00 into 10 raised to power minus 3 meter in the example of subtraction. They do not convey the precision of measurement properly. For addition and subtraction, the rule is in terms of decimal places. Now, rounding off on the uncertain digit. The result of computation with approximate number which contain more than one uncertain digit should be rounded off. The rule for rounding off number to the approximate significant figure are obvious in most cases. A number 2.746 rounded off to the 3 significant figure is 1.75, while the number 1.743 would be 1.74. The rule by convention is that the preceding digit is raised by 1 if the insignificant digit to be dropped is more than 5 and is left unchanged if the later is less than 5. But what if the number is 2.745 in which the insignificant digit is 5? Here the convention is that if the preceding digit is even, the insignificant digit is simply dropped, and if it is odd, the preceding digit is raised by 1. Then the number 2. 2.745 rounded off to three significant figures becomes 1.74. On the other hand, the number 2.735 rounded off to the three significant figure becomes 1.74 since the preceding digit is odd. In any involved or complex multi-step calculation, you should retain in intermediate step one digit more than the significant digit and round off to proper significant figure at the end of the calculation. Similarly, a number known to be within many significant figures such as in 1.99792458 into 10 raised to power 8 meter per second for the speed of light in vacuum is rounded off to an approximate value 3 into 10 raised to power 8 meter per second, which is often implied in computation. Finally, remember the exact number that appears in formula like 2 pi in t is equal to 2 pi into L upon G have a large infinite number of significant figures. The value of pi is equal to 3.1415926 and so on is known to a large number of significant figures. You may take the value as 3.142 or 3.14 for pi with limited number of significant figures as required in specific cases. Now the next point is, if a set of experimental data is specified to n significant figures, a result obtained by combining the data will also be valid to n significant figures. However, if data are subtracted, the number of significant figures can be reduced. For example, 12.9 gram minus 7.06 gram, both specified three significant figures, cannot properly be evaluated as 5.84 gram but only as 5.8 gram, as uncertainties in subtraction or addition combine in a different fashion. Another most important point, that relative error of a value of number specified to significant figures depend not only on n but also on the number itself. For example, the accuracy in measurement of mass 1.02 gram is plus minus 0.01 gram, whereas another measurement 9.89 gram is more accurate to plus minus 0.01 gram. The relative error is 1.02 gram is plus minus 0.01 upon 1.02 into 100, and this becomes equal to plus minus 1%. Similarly, the relative error in 9.89 gram is plus minus 0.01 upon 9.89 into 100, and that also becomes plus minus 0.1%. Finally, remember that intermediate result in multi-step computation should be calculated to one more significant figure in every measurement than the number of digits in the least precise measurement. These should be justified by a data and then the arithmetic operation may be carried out. Mass 1 dimension in length and minus 2 dimension in time. The dimension in all other base quantities are 0. Note that in this type of representation, the magnitude are not considered. It is the quantity of the type of physical quantity that enters. Thus, a change in velocity, initial velocity, average velocity, final velocity and speed are all equivalent to in this context. Since all these quantities can be expressed as length upon time, their dimensions are length upon time, that is L upon T or L T raised to power minus 1. Now the dimension formula and dimension equations. The expression which shows how and which the base quantities represent the dimensions of a physical quantity is called dimensional formula of the given physical quantity. For example, the dimensional formula of the volume is MLT, that is M is 0, L cube, T is 0, and that of the speed or velocity is M0, L, T is raised to power minus 1. Similarly, M0, L, T raised to power minus 2 in the dimension formula of acceleration, and M0, L minus 3T is 0, that of the mass density. An equation obtained by equating a physical quantity with this dimension formula is called dimensional equation of the physical quantity. Thus, the dimensional equation of the equations which represent the dimension of a physical quantity in terms of a base quantity. For example, the dimensional equation of volume, that is V, speed, force and the mass density can be expressed as in volume we have length cube, in velocity or speed we have t raised to power minus 1, force we have t raised to power minus 2, and rho, that is mass density, is L raised to power minus 3. The dimension equation can be obtained from the equation representing the relation between the physical quantities. The dimension formula of a large number and a wide variety of physical quantities derived from the equation representing the relationship among other physical quantities and expressed in terms of base quantities are given in Appendix 9 for your guidance and ready reference. Dimension analysis and its application. The recognition of concept of dimensions which guide the description of physical behavior is of basic importance, as only those physical quantities can be added or subtracted to have a same dimensions. A thorough understanding of dimension analysis helps us in deducing certain relation among different physical quantities and checking the derivation, accuracy, and dimensional consistency or homogeneity of various mathematical expressions. When magnitude of two or more physical quantities are multiplied, their units should be treated in the same manner as ordinary algebraic symbols. We can cancel identical units in the numerator and denominator. The same is true for dimension of a physical quantity. Similarly, physical quantity represented by symbol on both sides of a mathematical equation must have the same dimensions. Now, checking the dimension consistency of equation. The magnitude of physical quantities may be added together or subtracted from one another only if they have the same dimensions. In other words, we can add or subtract similar physical quantities. Thus, velocity cannot be added to force, or an electric current cannot be subtracted from the thermodynamic temperature. This simple principle, called the principle of homogeneity of dimensions, in an equation is extremely useful in checking the correctness of an equation. If the dimensions of all the terms are not same, the equation is wrong. Hence, if we derive an expression for the length of an object, regardless of the symbol appearing in the original mathematical relation, when all the individual dimensions are simplified, the remaining dimension must be that of length. Similarly, if we derive an equation of speed, the dimension on both the sides of equation, when simplified, must be of length upon time, or L t raised to power minus 1. So this is about the chapter 1. I hope you like the video. If you like the video, please like, comment, share and subscribe the channel. Thanks for watching.